In the last video, we defined what the Laplace transform of function is. We did a couple examples, and then we produced conditions which would guarantee that the Laplace transform of a function exists. Those two conditions were that the function had to be piecewise continuous on every finite interval and of exponential order, alpha. I would like to start this video by calculating two more Laplace transforms. And the first one is find the Laplace transform of t to the n a non-negative integer. We did last day the Laplace transform of t. So I'm interested in the Laplace transform of 1, which would be when n is 0, and t squared and t cubed and so on. And it is done in the book by integration by parts. It's set up the integral 0 to infinity e to the minus st t to the n dt. And I performed one integration by parts to knock the power of t down to n minus 1. I did another integration by parts to knock it down to n minus 2. And then I saw a pattern coming, and I said, if one follows the pattern, one gets to, and we got the final answer. I don't want to do it that way. You can read that one. What I'm going to do is something I know you're really going to love, okay? I'm going to suggest that the answer is n factorial over n to the n plus 1. You can see now why n has to be a non-negative integer, because if n were 3 halves, I have no idea what 3 halves factorial means. Now in the exercises, it actually does do that. It considers the possibility of n being a half or 7/3 and things like that. And this guy gets replaced by what's called the gamma function. So if you're interested in that, go to the exercise that's got it. I would like to do this a different way. I'm going to say, suppose we think this is the answer, all right? And we want to prove it. Now, one way would go derive it like in the book. But if you want to prove it, I'm going to try proving it by mathematical induction, because I know you love mathematical induction and want to see it again, right? So if we're going to use mathematical induction, the first thing we do is talk about n equal to 0. Is this formula correct for n equal to 0? So we would say, well, if n is 0, we're taking the Laplace transform of t to the 0, which is the Laplace transform of 1. And by definition, that's the integral from 0 to infinity of e to the minus st times 1 dt. And that's equal to antiderivative e to the minus st over minus s from 0 to infinity. And provided s is greater than 0, then this one will go away. And what will you be left with? The lower limit, you put in t equal to 0, you get 1, and you get 1 over s. Is that this if n is equal to 0? 0 factorial, 1. Yes. Therefore, true for n equal to 0. Not quite as trivial as the mathematical induction you saw for here. It was usually obvious that it was true for the first guy. What do we do next with mathematical induction? We say, assume result valid for some integer k. That is, assume that the Laplace transform of t to the k is equal to, what does it say? Put in k factorial over s to the k plus 1. That's the result, all right, that we're trying to prove, that this is the result. So I'm assuming for k, I'm dropping the k's. Now say, now prove for k plus 1. That is, what are you going to prove? That the Laplace transform of t to the k plus 1 is equal to k plus 1 factorial over s to the k plus 2. We can prove this, and we can say by mathematical inductions, it is true for all n. All right. Let's start with the left. The Laplace transform of t to the k plus 1. By definition, integral 0 to infinity t to the k plus 1 e to the minus st dt. That's its definition. What am I going to do with it? I'm going to integrate this by parts. Once. Not like in the derivation in the book, where I integrated it twice by parts, and then said if one carries on with a whole bunch more integrated by parts, one gets. We're going to have to do it once here. Right? So I'll call this one the u, and this one the dv. So the du is equal to k plus 1 t to the k. And the v is going to be equal to e to the minus st over minus s. All right, so what do we get? We get the integral 0 to, well, we got a term up front. You get u times v, that's t to the k plus 1, times v, e to the minus st over minus s. That to be evaluated 0 to infinity, minus the integral 0 to infinity of v, e to the minus st minus s, du, k plus 1, t to the k, dt. There's what the integration by parts is going to give us. Right, let's look at those two terms. If you look at the first term, I don't have any problem with this. If I put t equal to 0, it's gone. What about infinity? Infinity. This one's going to infinity. This one is going to infinity if s is less than 0. But just like we've done so many times before, if s is positive, this will go to 0. This will go to infinity, but the exponential goes faster. Based upon our experience with infinite sequence and series, we kind of saw that. So this is going to go away, provided s is bigger than 0. Now let's look at this one. For this one, let's cancel the minuses and pull out the k plus 1. Pull out the k plus 1. Pull out the s in the denominator, and what's left? 0 to infinity of e to the minus st, t to the k, dt. Right? Pull out the k plus 1, pull out the s, left with the exponential, and t to the k. But what's this? What is that? I assumed the result was true for k. What did I assume? I assumed that the integral 0 to infinity e to the minus st, k, t to the k, dt was equal to this. That's exactly what's sitting there. So for the box, I can put in him. So I'm going to have it. K plus 1 over s, and then for the box, I'm putting k factorial over s to the k plus 1. What have I got? K plus 1 factorial over s to the k plus 2. And that's exactly what I wanted to prove. That is what I want to prove, and we did it. And therefore we can say, therefore, result valid for all n greater than or equal to 0 by mathematical induction. Now here again, meaning integers. All right? So there's an alternative. But again, mathematical induction requires that you think you know what the answer is, and then you prove it. What the book did, it simply said, I don't know what it is, I'm going to derive it. Right? But I thought you might be interested in seeing both approaches. what I now like to do is calculate one more, right? And in the process, try to convince you of something. I want to calculate the Laplace transform of the sine of AT. Now remember I said in the last video that the functions we saw in chapter 15 were powers of t. We just did him. E to the ATs, did that last day. Sine ATs and cosine ATs, here they come. And then we'll have to worry later about, well, what if you multiply them? What if you've got e to the 5t times this? Or you get t squared times this? Coming, all right? We saw those at 15. We're just not quite ready for them yet. What I'm going to do is the following. Basically the same thing as is in the notes. One way to do it would be to set up the integral. Say, all I have to do is evaluate integral 0 to infinity e to the minus st, the sine of at dt. That's the definition of the Laplace transform of that function. But you'll remember from first year, if you want to do that one, you do integration by parts twice and reproduction. And I leave you to do it, but ask you to do it one of the exercises to confirm, right? I'm going to show you a different way. Much faster, and I'm going to get extra stuff that I'm not going to get if I do it that way, right? And try to convince you of what I'm doing is valuable. What I'm going to remind you of is Euler's identity. That was the cosine of AT plus I, the sine of AT. Remember, we've run into that on various occasions in the course before. One thing I didn't do, and I think you should do, is prove this with series. Write down the Maclaurin series for this guy, write down the Maclaurin series for that guy, write down the Maclaurin series for that guy, and ask yourself, does this one, these ones, add up to that one? That's a good exercise, and it works, giving you some kind of proof that Euler's identity is acceptable. First year, we simply threw it at you. You can actually prove it using infinite series. Try it. All right. So, noting that this is a part of that, what I'm going to do is I'm going to calculate the Laplace transform of ATI instead. Right? Because this one contains this one and contains that one. So if I do this, I'm going to get the Laplace transform of this one and this one. 2 for 1. And it's going to be much easier. No integration by parts. All right. So let's try it. By definition, this is integral 0 to infinity e to the minus st e to the ATI dt. That's what to be measured. Now notice we are working with complex numbers. All right? I said before that S would be real for us. I'm working with complex numbers, and I'm trying to convince you in this problem that complex numbers can be extremely valuable in this part of the course. So I'm trying to convince you now so that you won't be adverse to using complex numbers. They can make many problems much simpler. All right, let's go and evaluate. Integral 0 to infinity, e to the, let's write, minus s plus ai times t dt. Let's anti-differentiate. Antiderivative, e to the minus s plus ai t over minus s plus ai between 0 and infinity. All right. I don't have any problem substituting t equal to 0. It's the infinite limit of doing this. So let's rewrite this, break it back down into this and that, and say this is e to the minus st. Right? Thinking of this as e to the minus st e to the minus ai. Oh, wait a minute. Oops, I made a mistake, right? When I wrote this there, this one should have been a minus. This one, therefore, should be a minus, right? All right. So now this one's going to be, all right, so I'm breaking this one back up to e to the minus st, and it's going to be e to the a t I. And for this one, I'm going to put this. So we'll have cosine a t I sine of a t all over, what do we got on the bottom? Minus s plus a I and 0 to infinity. Now let's look at the infinity. If we go to infinity, what does this do? Oscillates back and forth between plus and minus 1. What does this one do? Same thing. What does this one do? Answer? If we chose s to be bigger than 0, this is going to squash all of that. And so that is going to go away at infinity. If we choose s to be bigger than 0. So if s is bigger than 0, all of that is gone in the limit st goes to infinity. And what are we left with now? To put in t equal to 0. Put in t equal to 0, there you get 1. Put in t equal to 0 here, you get cosine of 0, 1. Put in 0 here, you get 0. And then you've got that one, but because we're at the lower limit, we're subtracting s plus ai. So we get that. So what I've got now is that the Laplace transform of this guy is equal to that guy, which I kind of would have thought about. Remember, we had the Laplace transform of e to the at was equal to 1 over s minus a. And then looking at oh, I screwed that up again. This minus sign here, I forgot it again. Minus. Well, I saw that. All right. Because now, if I compare that being equal to that, doesn't it look reasonable based upon this? All we're doing is going from here down to here is put in ai instead of a. So that suggested to me that I made that slip. All right. All right, so what I'm going to write now, for this, I'm going to put in Euler's identity. The Laplace transform of cosine at I sine of at is equal to 1 over s minus ai. That's what I've proved. No integration by parts. Just integrated, no problem. What I want to do is I want to take the real part of the left-hand side, put it equal to the real part of the right-hand side, the imaginary part of the left equal to the imaginary part of the right. We saw that in 1210. You can do that. But I need this one to display the real and imaginary. Right now I can't. What if I were to multiply top and bottom by s minus ai? You did that in 1210. So you'd have then s plus ai over s squared plus a squared. And so now taking real and imaginary parts, I get the Laplace transform of the cosine of at. And on the left is the real, on the right it's s over s squared plus a squared. Imaginary part, Laplace transform of sine of at equal to e over s squared plus a squared. And so again, we got 2 for 1. By using complex numbers and Euler's identity, I not only got the Laplace transform of this guy, all right, I got the Laplace transform of that guy too, at the same time, with no extra work. If I had done them separately, by definition, I would have had 4 iterations by parts, 2 reproductions, in order to get this. This, no integration by parts at complex numbers then, very useful. And here's our first example. We define what it means to be the Laplace transform of f of t. We called it big LS. It's going to be absolutely necessary for us to do the opposite. That I give you an f of s, and I say, what are you the transform of? It's like differentiation the first year. You learn how to differentiate, you took functions of f of x, and you differentiate. At the end of the course, you came along and you reversed it. You talked about antiderivatives. I give you a function here and I say, who is his antiderivative? Who differentiates to give him? Same idea here. We say that f of t is the inverse Laplace transform of f of s if the Laplace transform of f of t is equal to the f of s. Right? So we call this guy the inverse transform of that guy. If his transform is this, then his inverse transform is that guy in there. Simply going backwards. All right? Now there's a bit of a problem. All right? Okay, if. And we write that f of t is equal to inverse transform of f of s. Remember that notation? Not meaning power, okay? Just like we have inverse tan, tan with a minus 1 up there. That's inverse tan, that's not tan with a minus 1. Right? So we use the same notation, and you have that in the first year when you talk about inverse functions. If this is a function, then the inverse function is denoted that way. It's not a power, right? Same kind of notation here. But there's a bit of a problem with it. Is the following statement correct? A function f of t has exactly one transform. If I give you an f of t, all right, the Laplace transform of a function f of t. Is there one or could there be more? Can a transform, a function, have more than one transform? And the answer is no. The transform is defined as a definite integral. And you cannot have two different answers to a definite integral. So the Laplace transform of f of t is unique. There's one and one only transform of a function f of t. But now I ask you the reverse. How many inverse transforms would a function f of s have? How many functions would there be whose transform is that? And the answer, an infinity of them. An infinity. And this presents a big problem. Now let me illustrate. Suppose I draw the following function, t and f of t. being equal to t squared. There it is. All right? What's its transform? Oh, we had in the board a little while ago that the Laplace transform, that doesn't look like no, that the Laplace transform of t to the n was equal to n factorial over s to the n plus 1. That's a formula we proved a short while ago. So therefore, the Laplace transform of this guy is 2 factorial over s cubed, 2 over s cubed. All right? That's his transform. Let me change the function into the following. Same picture. But what I do is I say, I'm taking this guy off. I'm moving him up to here. I'm taking this guy here off, and I'm giving no value. And I ask you, what's the Laplace transform of that function, if we call it g of t? What's his Laplace transform? I claim it's that same thing. That g of s is equal to 2 over s cubed. Do you agree? Well, how would you talk about the Laplace transform of this way? You'd say, set up the integral. And you'd have to integrate from here to here, and then integrate from here to here, and then integrate from there to there. Aren't you going to get the same thing as the integral if you do this one? Well, you take a point off or move it. Does that change the value of an integral? And the answer is no. And I can do that to any finite number, even an infinite number, as long as I'm careful with lumping, right? You can change any number of points here any way something you want, and you'll still get the same transform. So this guy, like this guy, is the inverse of that guy, and this guy is the inverse of that guy. So we've got an infinite number of inverse transforms for a given f of s. All right. Wonderful. But there's a big difference. This one is continuous. This one is not. So the question might be then, how many continuous inverses are there? And the answer, 1. There's only one inverse transform that's continuous. You cannot produce another curve over here, another g of t that's continuous, that will have the same transform. So as long as we're looking for continuous inverse transforms, there's only one. Are we looking for continuous functions? Remember what we're going to do? We're solving differential equations. Do all differential equations have continuous solutions? And the answer is yes! Thank goodness! Right? All the differential equations, even first order ones and higher order ones, have to be continuous. Even if you got these linear ones with these non-homogeneous or discontinuous, they're discontinuous, the solution will be continuous. So as long as we're sticking in the confines of differential equations, then there is one and only one continuous inverse, and he's the guy that we want. So we don't have a problem. If you're talking about other things besides differential equations, then you could be in trouble. Now you would have more than one transform, inverse transform. We don't. All right. Couple of quick properties. In fact, I already used one of them. L and inverse L are linear operators. I actually used that when I derived the Laplace transform of the cosine function. What does that mean? It means that the Laplace transform of f plus g is equal to the Laplace transform of f plus the Laplace transform of g. Remember that linear operator stuff we talked about back in chapter 15? Same idea. And that the Laplace transform of CF would be C times the Laplace transform of F. So that's what you would mean by the Laplace transform being linear. For the inverse transform, we'd have the inverse transform of f of s, let's just call it f and g, would be the inverse transform of f plus the inverse transform of g. And finally, the inverse transform of CF would be equal to C times the inverse transform of the F. Those are properties for linear operators back in chapter 15. We're simply saying that they are here. Well, certainly these are obvious because what are Laplace transforms? They're integrals. And integrals satisfy those properties. And if the Laplace does, then it quickly follows that so does the inverse. So it means if you wanted to take the Laplace transform of some of things, then you do them individually. If you want to take the inverse transform of a sum of things, you do them individually. Let's do a couple of inverses here. What is the inverse transform of 1 over s plus 4? Well, what you're going to remember is that Laplace transform of e to the at was 1 over s minus a. So what's that telling you? Isn't that telling you that this is e to the minus 14? Simply going backwards, right? Equivalent to this is that the inverse transform of 1 over s minus a is equal to e to the at. These two say exactly the same thing. One written in terms of transform, the other written in terms of inverse transforms. I don't go around writing these. I do enough work with Laplace transform, so will you, that this one is automatic in the power. I don't need that one. I see this one when I see that one. What is the inverse transform of s over s squared plus 5? Well, I better not use 5 because my 5s look like my s's. Okay, so let's put in here a 6. Well, what you have is, we did the sine and the cosine a minute ago. Wasn't the Laplace transform of the cosine of at equal to s over s squared plus a squared? So what do we got? We got the same thing, all right? We've got this with a 6, so if we go backwards, this is going to be equal to cosine of the square root of 16. Right? One more, because this was a little trickier. What's the inverse transform of 3 over s squared plus 6? Well, what we need to know is, what was the transform of the sine of at? It was a over s squared plus a squared. Well, we got the same kind of thing in here. 3, hey, this is a linear. Pull the 3 out. Now take the inverse transform of this. Well, that's looking exactly like this, right? So the a is going to be the square root of 6, but we don't have this a on top. So what do? We write 3 over root 6, the sine of root 16, right? In other words, what we're saying is, this a you could put it right there, right? I'm not going to do it, but I could. Right? So I need to fix up this root 6. So there's a couple inverse transforms. I have a couple more here I want to do. To really impress you, perhaps not the best word, to really get you to think about something. Suppose I asked you for the inverse transform of 1 over s squared plus 2s minus 8. We have not seen any transforms in our so far with s squares in the bottom, except the sine and the cosine. But the sine and the cosine ones didn't have this 2s term. So we've got a bit of a problem. We'll talk about that in a minute. Oh, notice that that factors into s plus 4, s minus 2. Does that give you any idea of what we might do? And the idea that should come to mind is, why don't we partial fraction that thing inside the braces equals the inverse transform of something over s plus 4 and something over s minus 2. Number. Oh, then it's going to look like that exponential one I did a minute ago and I erased it. So if we get the partial fraction decomposition here, we'll be able to finish. How do we get it? Since we've got non-repeated linear factors, remember when we were doing series and we were doing differential equations, there's a fast way to it. You want to know what's on top of s plus 4? Put your hand over it and put in minus 4. Minus 1 over 6. Want to know what's on top of this one? Put your hand over it and put in 2. 1 over 6. So if I bring that to common denominator, I should get 1. Now we can do it. We can bypass the minus 1, 6 and say, who transform is 1 over s plus 4? And the answer, e to the minus 4t. Same thing here, bypass the 1, 6. This is going to be e to the 2t. Done! Partial fractions was the key. In fact, I will now say that partial fractions are absolutely indispensable for Laplace transforms. If you do not know how to do partial fractions, you will not survive different Laplace transforms. Okay? Every time you turn around, it's partial fraction, partial fraction, partial fraction. So make sure you are an expert on partial fractions. Now notice, if I change this problem ever so slightly, suppose I make that a plus 8. Does that affect it? The answer is yes. That doesn't factor anymore. It's got complex roots. What am I going to do now? Answer, I don't know yet, but we will find out. What if it was this? If I had 1 over s to the 4th, I can do that because I know the transform of t to the n. I just have to reverse it. But what if it were s minus 1 to the 4th? What now? And don't say partial fraction or I'll shoot you. Okay? Partial fraction breakup of that thing, if you go through it, you get it back again. It's already there. In other words, I don't know how to handle that one either. This section of 6.1 is all about finding Laplace transforms using the definition. If we're going to do Laplace transforms effectively, we've got to find better ways of calculating transforms and inverse transforms. Just like in first year. You had a definition for derivative. Did you ever use it? Well, yes, you did, because somebody forced you to do it at least once. But then you gave you a bunch of rules. Power rule, product rule, quotient rule. So you didn't have to do it anymore. Right? Same with integration. Integration, much more difficult. Defined to be the limit of a sum. You're lucky if you did one example with it. But then you learn, oh, if you take an antiderivative, substitute the endpoints and subtract, you get the right answer. The same thing is going to be true here. I'm forcing you to the definition of 6.1. In 6.2, we're going to find many, many formulas that will negate the necessity of doing integration. We'll be able to use these tricks to find Laplace transforms easily. So it's just like that idea in first year. There's a theorem that says the following. If f of s is the Laplace transform of a function. Piecewise continuous function f of t of exponential order e to the alpha t. Then the following is true, that the limit as s goes to infinity of f of s must be 0. And I leave you to read the proof of it. What I want to suggest is this is an excellent way to make a quick check when you calculate a Laplace transform. We're going to be solving differential equations with Laplace transforms. And I'll show you that eventually, if not sooner. All right? And so you'll end up with a Laplace transform or something. And if it looks like this, you know you made a mistake. Does the limit of this thing as s go to infinity 0? No, it's a third. Therefore, you go back and check and say, hey, where did I make a mistake? And how long did that take? 2 seconds to decide that I was wrong. If I had this, then fine. That could be right. All right? It's not saying it's the correct answer, but it's saying it's definitely not wrong. Okay? That one is definitely wrong. Right? So use that when you're solving problems. Take a look at your answers and ask that question in 2 seconds. Is it going to 0 as s goes to infinity? It's a brief check, right? In the book, the notes, I gave in this section, really to satisfy some mathematicians, an example of solving a differential equation by Laplace transforms. We don't yet have the tools, so I had to quote a couple formulas that said, I'll prove these later. And I showed how to do it. I'm not going to show you that, all right? I don't care whether you look at it. We're going to get around to in section 6.3, 6.4 of solving dozens of differential equations. So to introduce it now, read it if you like to get a feel for what will go on later, or just ignore it until we get to it later. That finishes section 6.1. Right?